Thank you very much, Mario, for the introduction. Before starting, I'd like to thank the organizers, so Jen, Kaitlin, Mario, and Jesus for suggesting this very nice online seminar. It's a very good initiative. I think it's good to reach with other people. So I'm really glad, and I thank you very much for this nice initiative. So without further ado, so let's start this presentation. What I would like to discuss today is a new way we have suggested to analyze reactions involving halonuclei using an effective field theory to describe halonuclei, which is also known as halo EFT. So the idea started a couple of years ago following a discussion we've had with Daniel Phillips from Ohio University and Hans van der Hammer from the TU Darmstadt during a workshop in Trento. And then we have expanded this idea to breakup reactions, low, intermediate energy, high energy, and also to transfer reactions. So what I'm going to show today is this extension to various reaction models. And most of the calculation I will show you, I've not performed them myself, but they have been performed by grad students or postdocs, so including Laura Moschini, who was for postdoc in Brussels for 2 years, and now she's at the University of Surrey as a postdoc in the reaction group. Some of the calculations were performed by Chloe Bourne, who finishes her PhD in Brussels, and others, the one on transfer, were performed by Jie-Cheng Yang, who graduated in December last year. So in this presentation, I will first start with a brief introduction on halonuclei and the reactions that are used to study their structure. Then I will move to exactly this effective field theory description, and I will apply it in particular for carbon-15 because it's a nice nucleus to apply that description. And then I will move to the result of the reaction calculations we have performed, so transfer, Coulomb breakup, and also radiative capture on carbon-15. And I will show an extension that we have more recently performed on knockout reactions that looks also promising. And I will finish with a summary. So halonuclei are exotic nuclear structures found far from stability. So the development of radioactive ion beam facilities in the mid-80s has enabled the access of the nuclear physics community to unstable nuclei, and some of these nuclei have shown to exhibit these very peculiar quantum structures. So they exhibit a much larger radius than the isobars. And this large matter radius is understood as the fact that these neutron-rich nuclei exhibit a low separation energy for 1 or 2 neutrons. And because of that low binding energy, these valence neutrons decouple from the other nucleons in the nucleus and tend to have to wander away from the core of the nucleus. And so through the usual, the purely quantum tunnel effect, they exhibit a high probability of presence from the other nucleons. So you can see them as a compact core to which 1 or 2 loosely bound neutrons are loosely bound, and therefore form a sort of a diffuse halo around that compact core. So where are these nuclei, halonuclei? This is the lower left corner of the Segre chart. So you have proton numbers in the vertical axis, neutron numbers on the horizontal axis. Each square is a nucleus. The black squares are stable nuclei, and then the color ones are either beta minus or beta plus unstable. And So when you go away, you can, some of these nuclei exhibit these halo structures, so like barium-11 or carbon-15. I will mostly study carbon-15 in this presentation. So this is seen as a carbon-14 core to which one neutron is loosely bound. Then you also have two neutron halo nuclei. Mario Gomez 2 weeks ago discussed a lot about lithium-11, which can be seen as a lithium-9 core plus 2 neutron. And these two neutron halo not only have a very exotic halo because they have 2 neutrons in the halo, but they also are what is called Borromean structure. So the three bodies system is bound. So lithium-9 neutron and 2 neutron is bound, but the lithium-10 and of course the dineutron are unbound. And I think that Anna Corsi will discuss about that next week. So these exotic systems, because you have these diffuse halo around the compact core, are a significant challenge for nuclear structure models, which usually assume that the nucleus is a compact object. And so it's important to better understand the nuclear structure at the stability and beyond what is this, how that structure appears, and learn more about these nuclei. The problem is because they are far from stability, they are short-lived. So for example, carbon-15 has a half-life of 2.5 seconds. It's not unrealistic to perform experiment with that. It's not such a short half-life, but still it's not something you could not perform, make a target out of them, and then do electron scattering, for example, to get charge distribution. That's not something you can do. So in order to probe their structure, basically one of the nice ways to do it is to use reactions. And in this presentation, I will focus on 3-4 different kind of reactions. The first one is the transfer reaction, where you would start from carbon-14, fire a deuterium on it, and then you transfer the neutron from the deuterium to the carbon-14 to form carbon-15. And transfer reactions are known to provide accurate information about the spectroscopy, one particle, one nucleon spectroscopy of nuclei. So that's typically 4 halonuclei. That's an ideal tool. Another way is because these systems like carbon-15 are very loosely bound, they can be easily broken up. And the idea is you produce them at your favorite radioactive beam facility. It can be RIKEN, GSI, whatever, and you fire it on a target such as lead, and due to the interaction and because the system is loosely bound, it can be easily broken up in its core and the neutron, which you can detect in coincidence, and then from there you hope to get some information about the structure of the nucleus. Another reaction is the knockout. It's another type of breakup. It's a breakup, but it's inclusive in the sense that you do not measure the neutron in coincidence after the reaction. So what happens is that either the neutron breaks up elastically, so as a diffractive reaction, or it is absorbed by the target. You don't care about what happens, you just measure the core in coincidence, and then you hope there again to learn something about the structure of the nucleus. A fourth reaction, which is not directly used to study the structure of the system, is the radiative capture. In this particular case, it's because it has some astrophysical interest. That's something that Andrew mentioned 2 days ago in his presentation. So that's something that has been measured and which we have looked also in particular for this nucleus. So in order to infer valuable information about the structure of these systems, you need a good understanding of the reaction mechanism. So you need a good reaction. You need a good reaction model. But the other thing that you need to know, is to know exactly what is the nuclear structure information that is probed during these reactions. So are you sensitive to the spectroscopic factor? Are you only sensitive to what's inside the nucleus, only to the tail? So these are the things that you need to better understand. And we have addressed that particular questions coupling precise reaction models with this halo EFT, which I will discuss in a minute. So we have started with beryllium-11 because there are loads of data on beryllium-11 with Dan Phillips and Hans Werner Hammer. but recently we have extended that to carbon-15, and this is with Laura Moschini and Jie-Cheng Yang, and this is something I would like to discuss today. So, because the problem is a complex, the reaction description is a complex problem, we usually start with a few body description of the reaction. So let's first have a look at the transfer reaction. So you assume a transfer where you have a nucleus A, and then you have impinging on that nucleus, you have another nucleus, which is a two-body system with a core and then a valence particle. And the valence particle is transferred for this incoming nucleus towards the target nucleus, which then form nucleus B as A plus X, and then this core, this other particle here, B, flies away. So in this model, you will assume that that there is no structure in these nucleus, at least in the model that I will discuss today, I will use today. So the bound states, the incoming bound states, and the final bound states are described in a single particle Hamiltonian using effective interactions VBX for the initial bound state and VAX for the final bound state. And the scattering are described using optical potential, so either in the incoming channel or in the outgoing channel where B flies off from, where the small b flies off from the big B, so this two-body system. Especially for transfer reaction, for DP reactions that I will discuss today. This is the post-form expression of the transfer matrix. So you have the three-body wave function, okay, for that, with that incoming wave function. You have the potentials here that lead to the transfer reaction, and this is the outgoing channel where A and N, so A and X in that case are bound, and B flies. So the proton that would be B here flies off this nucleus B. I will not use as fancy a model as what Mario has presented 2 weeks ago. We base ourselves on the Johnson and Tandy approximation. So it's the adiabatic distorted wave approximation, where this three-body wave function is approximated as the incoming distorted wave between the deuterium and the nucleus A, and then the bound state of the deuterium. Okay, I think Natasha will discuss early in May more precise model, and 2 days ago Andrew has mentioned a few things on transfer as well. I will not go into as precise models as these, but I will rely on that usual Jensen and Tandy approximation. So for breakup, it's similar. We also have a few body descriptions. So you have, in this case, the nucleus B under study, which is this core A plus one loosely bound neutron, which is impinging on a target, and then this two-body system breaks up into the core and the neutron. So this is shown here in this on the right in this plot, where you have the core, the neutron. That system there is described as a single particle Hamiltonian with an effective interaction that describes the interaction between the core and the neutron, which is used to compute the ground state wave function of the system. The target is seen as a structureless particle. We neglect its structure, and the interaction between the projectile constituents and this target are simulated by optical potentials. And so within that framework and within that Jacobi set of coordinates, we have to solve this three-body Schrödinger equation with the initial condition that the projectile is in its ground state and it's impinging on the target. At the energies considered here, so 70 MeV and 600 MeV per nucleon, the Eichner approximation is reliable. So we will use a dynamical Eichner approximation at 70 MeV per nucleon. That's something we have developed with Daniel Bay and Gerald Goldstein in 2005. And at higher energy, we need to include relativistic corrections. So I will use, we have used an Eichner approximation including relativistic corrections developed by Laura Moschini last year when she was in Brussels. So about carbon-15. Carbon-15 here is the lower energy spectrum of carbon-15. So the ground state is a 1.5+ state. It's just 1.2 MeV below the carbon-14 neutron threshold, so it has a significant carbon-14 neutron cluster structure. So we usually, in an extreme shell molecule, will describe that as a 1s½ neutron bound to a carbon-14 in its 0+ ground state. It also has a 5½ excited state, which is seen usually as a d bound state neutron. And what you see is that in the continuum there is not much, but for this 1/2- resonance, at least at low energy, there is not much here. So in usual reaction models, you would have this single Hamiltonian, so that's a kinetic term plus a potential, that's a local potential that simulates the interaction between the core and the neutron. Usually people would pick a Wood-Saxon potential and fit its parameter, the depth, the spin orbit strength, in order to reproduce what you know about the system. So the binding energy, the spin and parity of the different states, low energy states that you know, etc. And so in our case, the bound states that I've mentioned, so the 1/2+ ground state and the D5 and the 5½ excited state, would be described as eigenstates of this single particle Hamiltonian, which in partial wave LJM would are just eigenstate of this nucleus, and that the radial wave function has this famous exponential decay at large distances, and the normalization of that decay, is this asymptotic normalization coefficient, in short ANC, that characterizes basically the strength that you have in that tail, so that the magnitude basically of the halo, the higher it is, the higher the probability of the neutron being in the halo is. Now, that part, that Hamiltonian, also describes the low energy continuum. So in the continuum, you have just a continuum wave, which is phase shifted, compared to the plane wave. And that phase shift depends on the interaction that you put here, and it's also described by that potential. So what we use here is we replace that usual Wood-Saxon by an effective potential. And so we base the fact that in Halo EFT, you have this clear separation of scales between a small scale and a large scale. And you can see that in both energy and distance. So in energy, you have a tightly bound core to which you add a loosely bound neutron. So the binding energy of the valence neutron is very small compared to the excitation energy of the core. So you can basically neglect the high energy part of the mechanism. And if you want to look at that in the distance, so in the coordinate space, then what you would have is a compact core, so a small core, and then to which a diffuse halo, so that it extends at large distances. So you can see the separation of scale in the two point of view. And the idea of effective field theory in general is to say you can expand your Hamiltonian or your interaction onto a small parameter, which is a small scale divided by the large scale. And this idea was suggested by Carlos Bertolani, Hans Werner Hammer, and Bira van Kolk in 2002. There is in 2017, so 3 years ago, there was a nice review article published in Journal of Physics G on the subject. So the basic idea of this Halo EFT, because you do that expansion, is to assume that all the short-range physics is put under the rug, and that you don't care about that short-range physics. So you replace your interaction by a contact interaction. So we don't use a purely contact interaction. What we use is we use a Gaussian, so we regularize that contact interaction, and we have a Gaussian formed. The radius of that R0, which is the radius, the cutoff, if you want, the short range cutoff, the range of that Gaussian is chosen, is not a parameter that you vary in order to fit anything, but it's a way to evaluate the sensitivity of your calculations to the short range physics. So you change R0 and you see how sensitive you are to R0. and from there you can get some information. So at the leading order, you have just one term, which is this Gaussian, and one parameter, which is the depth of the Gaussian. And what you do is you fit to the most important parameter, which is the binding energy of the system. Usually that's known experimentally. Then it's a series expansion on that parameter. So there is a next to leading order term. And there you add the second order derivative from this contact term. So you have a second surface term that appears. So you have this time two parameters, and you can fit two values, two physical values. So the binding energy, that's one, and one is this ANC that is needed. So you need the ANC. So either you have a reliable nuclear structure calculation that predicts this ANC, like ab initio calculation for very 11, or if you don't have it, you need to extract it. And Jie-Cheng Yang, during his PhD, developed a nice idea to extract that reliably from the analysis of transfer reactions. So the idea that I will summarize here, the case we study is you look at these reactions, carbon-14 DP, so neutron transfer from deuterium to carbon-14. And what he has shown, what Jie-Cheng has shown, is that the reaction is purely peripheral. So you probe only the ANC of carbon-15. If you go to low deuterium energy, so lower energy reactions, and you look at forward angles. So you select your data at very forward angles. And so in order in his analysis, what he did is he started from a leading order calculation, and he used different R0. Okay, that's the wave function, the radial wave function that you see here as a function of the distance, and the different values of R0 from 0.6 to 2.0 Fermi. And what you see is that it generates a significant amount of different wave function with which you can perform these transfer reactions. And that's what he did. So he ran this finite range adiabatic distorted wave approximation, Johnson and Tandy. And here is the transfer cross-section as a function of the angle. And what you see is that very forward angle, you have a large sensitivity, and the curves order exactly in the same way as the square of the ANC. So the square of the magnitude here of the exponential table. And so in order to show that, he developed this sort of a ratio. So he takes the cross-section that he obtained from this ADWA calculation, divided by the square of the NC, and then he does a ratio of that cross-section to eliminate most of the angular dependence on one value that he takes as 1.4 when R0, so the cutoff, equals 1.4 Fermi, in order to be in the middle of this range of values. And that's this ratio here plotted as a function of the scattering angle. And what you see is that if you go really at forward angle, the sensitivity on the different values that you have nearly vanishes. So the two dotted lines here correspond to plus or minus 5% difference. And so if we took this place where the curves are within 5%, so up to 10 or 12 degrees in this present case, and we assume this is the place where the reaction is purely peripheral. And so what you can do now is compare to actual data, and from there extract an ANC that we can assume to be reliable. And that's what he did. So he compared each of the calculations that he has for each of these wave functions, so plotted and extracted an ANC by scaling his transfer calculation to the actual data. And so for each value of the R0, which are plotted here in the horizontal axis, he gets a different value of the ANC. And what you see is we get something rather flat. So here it doesn't look as flat, but the difference between these two curves is basically 2%. It's plus or minus 2%. So the difference is very small. So you have something which is very reliable. It means that you're not sensitive to the internal part of the wave function. You basically probe only the tail of the wave function when you select the data in that particular range. And so from there, he extracted an ANC, which is 1.26 plus or minus 0.02 Fermi power minus 1/2. And that's very close to the ab initio calculation performed by Peter Navratil. So at the time we performed the calculation, there was no ab initio calculation. And then Peter Navratil told us, oh, I have a calculation, I have a preliminary value for the ANC, and that's the value that he gets. So we get a very good agreement with the ab initio calculation, even though we did not interact with him when Jay Cheng did his calculation. So now we have everything we need. We have the binding energy, we have the ANC, we can fit the potential next to leading order. And so that's what we did. We got 3 different values of R0, and we got this. So here are these radial wave functions. So you have the same exponential tail. That's what we want, but different expression in the interior. So that's what also we want. So if our reactions start to be sensitive to what's going on inside the nucleus, then we will get different cross sections. That's for the S wave. In the bound state for the P wave, we assume that the potential is nil. Due to our experience in the barium 11, we assume that in this case, there is nothing to fit the P wave in the continuum. So we assume that the interaction is 0, that the phase shift will be very close to 0. So we will not have any interaction beyond. And we will test this on the different reactions, these assumptions on the different reactions we are going to study. So the first one, of course, is transfer. So that's a bit of a game, of a one game. Here are the wave functions we consider. Jay Cheng put them back in his transfer calculations, and he got these transfer cross section as function of the scattering angle. And what you see is that at forward angles where the potential, where the ANC was extracted, we have excellent agreement with the data. We also see that all the wave function provide exactly the same value. You start to see small differences at larger angles. That's an indication that you start to probe the internal part of the wave function. So this is for transfer. Transfer works fine. So what about Coulomb breakup? Coulomb breakup has been measured for carbon-15 in 2 different labs, RIKEN and GSI. So here is the breakup cross-section measured at RIKEN at about 70 MeV per nucleon as a function of the relative energy between the carbon-14 core and the neutron after dissociation. There are 2 sets of data because they have been measured at 2 different angular cuts. So the large angular cut, 6 degrees, and then forward angles, 2.1 degrees. That's the 2 different cuts that we see here. We used the dynamical Iconar approximation I have mentioned before. And so we have performed the calculation with the 3 different wave function I have mentioned before. What we see is that they all lie on top of each other. There is no difference. The green band corresponds to the small uncertainty, so the 2% uncertainty we have on the ANC. So that's what's given by this green band. So the fact that all the calculations fall on top of each other shows that the reaction is purely peripheral, which is something that we had already tested in another way with Filomena Nunes in 2007. So that's for the RIKEN data. This is the GSI energy, and we use, as I've mentioned before, the relativistic correction to the Iconar approximation developed by Laura Moschini when she was in Brussels. And here again, you see that all the calculations lie on top of each other. And so that there is no sensitivity whatever to the internal part of the wave function. A quick comment, the dashed purple line here correspond to the calculation where she doesn't put any relativistic correction. So this shows that you really need to include these relativistic corrections to extract something from these data. Now, the good thing is that these 2 measurements, sets of measurements, have been done by different people, different energies, and basically one description of carbon-15 fits all. So it's one size fits one model fits all. So we fit not only the transfer data that they've shown before, but also these breakup calculation here, and that confirms the value of the ANC that we have extracted, the hypothesis we've made to assume that the phase shift was nil in the P waves. And this has been published in this paper last year. So I now move to the radiative capture because this reaction has an interest in astrophysics. It's a reaction that can take place in some asymptotic in red giants in the asymptotic branch region. So reaction where the carbon-14 would capture a neutron to form carbon-50. And so it's important to have a model that reliably predicts this value. So here is the capture cross-section divided by the square root of the energy to remove the major dependence on the reaction. And what you see is that once more you are completely insensitive to R0, so to the range of the Gaussian that you use, because the reaction is purely peripheral. That's something we know, of course. And this value agrees very well with the ab initio prediction that Peter Navratil has extracted from his no-Cauchy calculations. How do they compare to data? Well, René Reifat and collaborators have measured that. There is an issue here because you have here, it's the neutron energy, that's the experimental cross-section, that's our cross-section. I don't put any data point here because the neutrons are not monochromatic, they have an energy distribution. So I prefer to put the theory cross-section average over the neutron density and then compare directly to what is obtained experimentally. And what you see is that above 100 keV, we have an excellent agreement with the data. We really fit the data very well. We have a problem at low energy. Other groups also have problems there. I don't know exactly what happens. So this is a larger cross-section than what our model predicts. But at higher energy, we perfectly fit the calculations, the experiment. Sorry, the experiment. So Chloe has now also extended the idea of this, including halo EFT in knockout reaction, and she had done calculation not on carbon-15 but on beryllium-11, which is our usual test case. So the idea is you send beryllium-11 on a carbon target, and then the carbon strips the neutron from beryllium-11, and what is left out is the core. Now you have this reaction, as I've mentioned before. This reaction can take place in two different processes. The first one is basically the breakup I've mentioned before. So the neutron dissociates from the core and flies away, but it's not detected, so you don't know what happens to that neutron. Or it is absorbed by the target, and there it's stripped. So you have two contributions to that reaction. You have the first one, it's just the diffractive breakup, and the other one is the stripping contribution. So you have to account for both to compare to data. And so she took three different wave function within this halo EFT idea. So that's the three curves that you can see here for the radial the radial wave function. So you see significant difference at short distances. Here are her results for the breakup cross section, the knockout cross section as function of the pi momentum of the core in the center of mass. And what you see is that the top curve, the dashed curve, at the diffractive contribution, so where basically beryllium-11 breaks up into beryllium-10 and the neutron, and they both survive the reaction, but the neutron is not detected. Or the stripping cross section is this series of dotted lines here, where the neutron is absorbed by the target. Both are about the same height, so you really need to include both in the comparison to the data. And what you see is that there is absolutely no difference between the different curves that you see here. So you have three curves, and there is no sensitivity. So what that means is that also for these reactions that are nuclear dominated, that with the contribution, the stripping, that is much less elastic than the diffractive breakup, even in that case, the reaction it remains purely peripheral. Now, one of the nice results that Chloe has obtained in her analysis is that these calculations seem to be very little dependent on how you describe the continuum. of the nucleus. So the interaction between the beryllium-10 and the neutron in the continuum, especially the P wave phase shift. And so it suggests that this would be an excellent probe to the ANC because you have very little dependence on the way you describe the continuum. So far we've not compared to data because that was the first step of the work. So it's an ongoing work. So we have no direct comparison with data yet. So hopefully in the future we'll come with something else. So with that, I come to the conclusion. So to summarize what I said is halonuclei are very exotic beasts, so it's very interesting to study them, but you need to do it mostly through indirect ways because of their short half-life. So it's mostly done through reactions. The mechanism of the reaction is rather well understood, but the question we wanted to address is how reliable are the structural information that you infer from these reaction measurements. And so what we did to try to answer that question is to use Halo EFT and couple it to a reliable model of nuclear reactions. And this really, because of it's a systematic expansion with terms that you added and that become smaller and smaller, you can have a very systematic way to include more and more degrees of freedom. So the ANC, the phase shift, the binding energy first, the ANC, the phase shift in the continuum, etc. Slightly step by step. And so we have done that. We have used that to study carbon 15. And so with one description of carbon 15 fitted on a very small number of parameters that are adjusted to something that we know, so binding energy and then the ANC, we could reproduce transfer reaction, Coulomb breakup at both intermediate and high energy, and also radiative capture, all three being reactions purely peripheral. What I've shown also is that what Chloe has shown is that the knockout is also a purely peripheral reaction. We were not fully sure of that. And so we hope that in the future we will be able to analyze knockout data and see if this description of carbon 15 that we have used here can also be used to describe knockout reactions. That would be an exciting result. We also plan to study other systems like NEN31 in particular. That's the next step. And at the in the longer term, we hope that we will be able to include more degrees of freedom in the structure of the nucleus, including core excitation in particular would be particularly valuable. So with that, I will end here. Thank you for being here. Thank you for joining us for this online seminar. And I would like also to thank my collaborators, so Hans-Werner Hammer and Achim Schwenk from the TU Darmstadt, Dan Phillips from Ohio University, and then Laura Moschini, who's now in Surrey, Zhejiang Yang, and Chloe Brun from the University of Brussels. Thank you very much.